let's revisit gas behavior. So I have a box, I have two particles, and they are very small in comparison with the size of each other, and they're very small in comparison to the size of the box. This means that the chances of them interacting is pretty slim. And later on, as we go through the chapter, we'll pin down what's called ideal behavior of that these particles basically don't interact with each other. Okay, the particles are in motion because the temperatures that we're looking at are above absolute zero, so everything has thermal motion, and gases have very high entropy, so they pick up motion, and the particle bounces off the wall. That collision is elastic, meaning that the momentum in is equal to the momentum out, and we don't even have to concern ourselves with the angle in that because the vector in is the same as the vector out, so everything will sort itself out. Okay, the collisions with the container wall happen with force. Force is mass times acceleration, and pressure is what those collisions exert. Pressure is simply force per area. And because force is in newtons and area is a two-dimensional aspect, that could be square meters. Newtons per square meter is a unit that we call the Pascal. Now the Pascal is a very, very small number. 1 atmosphere, the atmosphere is the unit of gas pressure that we used in chemistry 1, is 101,325 pascals. So pascals are a really, really small number. That number is also equal to 760 millimeters of mercury, which are also called 760 torr. Here's the problem with pressure, is that so many different branches of science and engineering use pressure. They all use their own peculiar units. The one that's rooted in the most SI, Standard Institute values, is the Pascal. So in previous terms, we'd use the atmosphere because it's easy. We're going to end up gravitating now towards the Pascal. Now there is another competing value that, because this 760 millimeters of mercury and 101,325 is kind of an ugly number, some rounding has happened that if you call that just 1 kilopascal, 100, oh, I've done that wrong, that's 100 kilopascals, because it's 100,000, there you go, or 750 torr, just round those numbers, that becomes a bar. Bars, of course, are used in meteorology, but we'll see them. But if we can stick to the Pascal, that's the best idea. Let's look at the factors that influence pressure. So a gas which is confined to a space, there are 4 factors. There's pressure, there's volume, there's the number of moles, and there's temperature. And each of these factors are interconnected. Pressure, we know, results from collisions. So if I were to do something like, let's look at this collision. This particle is moving, it has a collision, it moves on, it traverses across what we call free space, and then hits again, and then would bounce and bounce. And if we could count the number of bounces per second, that would give us a gauge of what the pressure is. If I went ahead and I made the size of the container smaller, then the particles would travel a shorter distance between collisions. The time between distances would be shorter. The number of collisions would therefore increase with time, and therefore pressure would go up. So pressure goes up when volume goes down. And we can think of these as cause and effect either way, that if I change the volume, I will change the pressure, or if I pressurize a volume, I will, if that has movable walls, then the volume will also change. Okay, so pressure goes up when volume goes down. That means that the pressure is proportional. This alpha here is a proportionality. It doesn't say equal, it says proportional to the inverse of volume. If I move the volume across the equation, then the product of pressure multiplied by volume is equal to a value. And that value is a constant, which means that under these conditions, the product of pressure and volume is the same as under those conditions. This gives us P1 V1 equals P2 V2, which is our most common way of expressing Boyle's law. But what Boyle's law really says is that this combination, this product here, is a constant value. And we did this in Chemistry 1 in lab, that we plotted pressure versus volume, and we found that that was a curve, but if we inverted the volume, then we found out that that's actually a straight line. There are a couple of other relationships that are so common and so well studied that they have become known as gas laws, that increasing the temperature makes the particles move faster. They have more kinetic energy. That increases the volume. So volume is directly proportional to temperature, which means that if I pull the temperature across this proportionality, it will go to the denominator position, so that volume divided by temperature is a constant. This gives us the basis for Charles's law that says V1 over T1 is equal to V2 over T2, because V over T is a constant. It's constant under one set of conditions, it's constant under another set of conditions. Similarly, that if I were to increase the number of particles inside the box, then I get more collisions. The number of particles is directly proportional to the volume. Volume is proportional to the number of moles. So volume divided by the number of moles is equal to a constant value. The Avogadro's rule can be written that V1 over N1 is equal to V2 over N2. This last one is actually quantifiable, that at standard temperatures and pressures, which is 1 atmosphere, which we won't be using anymore, but 101,325 pascals, and 0 degrees Celsius, so 273 Kelvin, because we don't use Celsius in gas calculations, that the molar volume, the volume for 1 mole of any gas, regardless of its identity, is 22.4 liters. Okay, so we've established these relationships, that the pressure volume product is a constant, that the volume to temperature quotient is a constant, and the volume to number of moles quotient is also a constant. What if you could combine all of these constants into one new value, into one new constant that expressed everything? This would be what's called an equation of state. It quantifies the 4 factors that tell us what gas behavior is into something neat and tidy. The PV divided by NT is equal to R. This is most often at the high school and undergraduate level rewritten as PV equals nRT, because it's all on one line. And reading things that are all on one line is inherently easier than reading things that are a fraction. But this is what PV equals nRT is all about, that these 4 factors are all controlled by this constant. Now, the universal gas constant, R, if you go look up its Wikipedia page, it shows you there's 20 different values, because it depends which value of pressure did I use, which value of units for volume did I use. Moles can only be moles, and temperature is always going to be in Kelvin, because we cannot use Celsius, because Celsius becomes a negative number, and any temperature that has a negative value, if I'm using it in a calculation, will force my other numbers, the value that I'm solving for, to also be negative. So these two are always the same, but pressure and volume, they can get to change. So the 2 common ones are R is 0.0821 liter atmospheres per mole per Kelvin. This is the one that we use in Chemistry 1 because it's the most straightforward. But the one that's better is that R equals 8.3144 pascals per cubic, not per cubic meter, let me say that again. R is 8.3144 Pascal cubic meters per mole per Kelvin. Okay, this is my pressure, that's my volume. Here the pressure is, the volume is usually written in front of the pressure, but doesn't matter as long as what's above the, what's in the numerator and what's in the denominator are clearly stated. Okay. Ideal gas behavior, or ideality, happens simply when this equation is obeyed. That if we were to plot this graphically, that we would be on a linear, predictable part of the graph. Now that's not true. Ideality doesn't happen completely across the board. It specifically doesn't happen when your gas samples are very cold. If you push them so cold that they start to want to liquefy, then the particles want to attract to each other. And that breaks one of the basic, there's only two conditions for ideality. That the volume of the particles themselves, the gas particles, is insignificant in comparison to the volume of the container, and that the interactions, either attractions or repulsions between the particles, also is insignificant. So when we cool things down, or when we push them into very, very small volumes, then we push away from ideality. So the most likely place to find an ideal gas is when it is in a very large volume and it is warm. Because our description of gases is so purely mathematical, we can look at gas mixtures using exactly the same math. If I have the same volume that I had before, and I now have 4 gas particles in there, but they're of 2 different types. Because we've already established that under ideal behavior, that the gas particles don't come near each other very often. They are far apart, and that when they do come near each other, they just have elastic collisions. They don't interact, they don't repel, they don't attract. Then each individual gas particle acts like its own individual particle. This is not a sample of gas. It is thousands and thousands of individual particles. It's a population, which is something that we'll delve into a little bit in a later chapter. So this gives us Dalton's law of partial pressures, that the total pressure exerted inside this container is the pressure of all of the pink particles plus the pressure of all of the black particles. And because PV equals nRT, then P equals nRT over V. So this is the number of moles of pink multiplied by R multiplied by T divided by V, plus the number of moles of black multiplied by R multiplied by T divided by V. And because R, T, and V are all the same for the system, the only 2 things that differ is the number of moles of the pink and the number of moles of the black. That's it. So another way of saying this is that the pressure of one of the components, so this isn't a true pressure, this pressure right here, the pressure of the pink, is what we call a partial pressure. So we put a little apostrophe there to let us know that this number belongs to another whole. It is a subset of the whole pressure. That the partial pressure of the pink particles is equal to chi, or x, of the pink multiplied by the total pressure. Chi of the pink, a chi is just a tall x, is what we call the mole fraction. Mole fraction is just like a percentage, only instead of being out of 100, it's just out of 1.00. Okay, so the mole fraction of the pink particles is the number of pink particles divided by the total number of particles. And because we only have two different types of particle in this particular question, that's the number of pink plus the number of black.